All right, so get ready because today we're going to dive deep into Physics of the Impossible by Michio Kaku. This book takes all those cool sci-fi ideas like force fields and invisibility, the stuff we love, and it uses actual physics to look at if those things could ever really be possible.
Yeah, it's a really neat way to look at things. And Kaku, he starts by saying that what seemed impossible in the past is just normal today.
Right. Like, I'm thinking about when I first learned about continental drift in school, the idea that all the continents were once smushed together and then slowly moved apart over millions of years. It seemed so crazy back then.
Yeah, exactly. And it's the same with that theory that a meteor wiped out the dinosaurs. It was a radical idea back in the day, but now, like everybody knows, that's probably what happened. So Kaku uses those examples to show how our understanding of the universe is always changing, and that what seems impossible now, maybe it won't be in the future.
Right. So don't dismiss those wild ideas too quickly because there might be some real science hiding in there. Okay, so how does he actually tackle all these impossibilities?
Well, he divides them into three classes. Class impossibilities are things that are impossible right now with the tech we have today, but could be possible in like 100 or 200 years. Stuff like force fields, invisibility cloaks, and even some kinds of teleportation.
Ooh, that's pretty exciting. So what about the really far out stuff? Like, could we ever harness the power of a star like a Type 2 civilization?
That'd be a class 2 impossibility, something that might take thousands or even millions of years to figure out. But like Kaku says, time is relative. What's impossible for us right now might be super easy for a civilization that's billions of years ahead of us.
Okay, I get it. So class 9 is within reach, class 2 is way out there, but maybe possible for some super advanced aliens out there. What about class 3? Is there anything that's really, truly, absolutely impossible no matter what?
Class 3 impossibilities are the ones that seem to break the laws of physics as we know them, like perpetual motion machines or knowing the future. But, and this is super important, Kaku reminds us that all through history, scientists have said things were impossible and then, boom, someone figures it out. So even those class 3 impossibilities, maybe they're not totally off the table.
I like that. It's a good reminder to keep an open mind, especially when we're talking about science. Okay, let's jump into some specifics. Force fields. Kimon, who hasn't wanted to deflect laser beams like they do in the movies, could we ever really make that happen?
Well, it might surprise you, but the idea of force fields actually comes from real science. It goes way back to Michael Faraday in the 1800s. He found out that if you move a magnet, you can create an electric current in a wire without even touching it. That showed that a magnet's field, which you can't even see, could affect things across empty space.
So that's like the starting point for force fields, right? Using fields to affect stuff from a distance. But how do we go from magnets and wires to stopping laser beams?
Well, Kaku says that a force field in the future would probably have, like, different layers of protection. One idea that's really cool is the plasma window. Imagine super hot plasma controlled by magnetic fields acting like a wall between two places.
Okay, that sounds intense. What would you even use that for?
Think about a spaceship flying through space. You got to keep the vacuum of space separate from the air inside the ship, right? A plasma window could do that, making an invisible barrier that's also super strong.
Whoa, that'd be wild to see. But plasma is crazy hot, isn't it? Wouldn't that be dangerous?
It definitely would be tough to control, yeah. But remember, we're talking about tech that might not be around for like decades or even centuries. If we can figure out how to control and contain super hot plasma, then there are a ton of possibilities.
It's mind-blowing to think we might one day be able to mess with matter like that. Okay, so plasma windows are one idea. What about other ways to make a force field?
Well, another idea uses a material that's already changing a lot of different fields. Carbon nanotubes.
Oh yeah, I've heard of those. They're like these super strong, tiny tubes, right?
Got it. They're basically sheets of graphene, which is a single layer of carbon atoms in this honeycomb shape, all rolled up into a tube. These carbon nanotubes are insanely strong, like 100 times stronger than steel, but only 1/6 the weight.
Wow, so you're saying we could maybe weave these nanotubes into some kind of fabric that could stop bullets or something. That's crazy.
It's still super theoretical, but the potential is there.
Yeah.
And nanotechnology is moving so fast, we're always finding new ways to manipulate stuff at the atomic level. Who knows what kind of wild materials we'll be able to make in the future.
Okay, so force fields might actually happen one day. That's pretty awesome. Let's move on to something even more sci-fi. Invisibility. Can we really make things disappear like they do in Star Trek?
Well, just like with force fields, invisibility might be closer to reality than you think. It all comes down to understanding how light and matter interact with each other.
I remember learning in school that light is made up of waves, but it also acts like particles. It's kind of weird.
It is weird, and it's that double whammy nature of light that opens the door to invisibility. See, when light hits something, some of it gets absorbed, some bounces off, and some goes through it. What we see is the light that bounces back to our eyes.
So to make something invisible, we'd have to stop it from reflecting any light at all.
Exactly. And there are a couple of ways we might be able to pull that off. One way is to play around with the index of refraction. That basically tells you how much a material bends light.
Okay, I kind of remember that from physics class, but how does bending light make something invisible?
Think about a mirage. When it's hot out and you're driving, and it looks like there's a puddle of water on the road.
Oh yeah, I've totally seen those. It's like the road is reflecting the sky.
You got it. What's happening is that the air near the road is hotter and has a different index of refraction than the cooler air above it. That difference makes the light bend, and it creates the illusion of a reflection.
So you're saying we could use that same trick to bend light around an object so it looks like it's not even there.
That's the idea. It's like making a mirage all the way around the object.
Wow, that's pretty clever. But how do you actually change the index of refraction on purpose? Do you need like a special material?
That's where things get super interesting. Scientists have made something called metamaterials. They're artificial materials that are designed to have properties that don't exist in nature. By carefully designing the structure of these metamaterials, we can control how they interact with light, including their index of refraction.
Okay, so metamaterials are like custom-made materials that bend light in specific ways. That's wild. Have scientists actually made anything invisible using these metamaterials?
There have been some pretty cool breakthroughs. Like a few years back, researchers at Duke University made a metamaterial that could bend microwaves around a cylinder. It made whatever was inside the cylinder invisible to those microwaves.
So not visible light yet, but still a huge step. What's holding us back from making things invisible to our eyes?
The problem is that visible light has a much shorter wavelength than microwaves. To mess with visible light, we need to control the structure of these metamaterials at an even smaller scale, like at the nanometer level.
Nanotechnology, building things atom by atom, sounds crazy complicated.
It is, but it's also a field that's moving super fast. As we get better at manipulating matter at the nanoscale, the chance of making metamaterials that can bend visible light becomes more and more real.
Okay, this is blowing my mind. So you're saying that invisibility cloaks like the one Harry Potter uses might actually be possible someday.
We're not quite at the point of making a whole person disappear, but some scientists think that we could have some kind of invisibility shield in the next few decades. Think about the possibilities.
This is incredible. Okay, I'm totally hooked on this idea of manipulating light and matter to create things that seem impossible. Let's talk about something even more powerful. The Death Star from Star Wars. Could we ever build a weapon that could actually blow up an entire planet?
Now that's a question that freaks people out and makes them curious at the same time, isn't it? The idea of having that much power is kind of scary, but also really interesting.
Well, I mean, we do have nuclear weapons, and those are pretty terrifying on their own. But even the biggest nuke is nothing compared to the Death Star.
You're right. To get that level of destruction, we need a way more powerful source of energy. Something like nuclear fusion.
Fusion, isn't that what powers the sun? The thing scientists have been trying to make work here on Earth for years.
Exactly. It's when you take hydrogen atoms and smash them together to make helium, releasing a ton of energy in the process. It's the same thing that happens in hydrogen bombs, just on a much, much bigger scale.
I remember reading that fusion is really hard to do because you need these crazy high temperatures and pressures. But what if we could figure it out? Could we actually build a Death Star?
Kaku looks into that very question. He says there's no physical limit to how much energy a hydrogen bomb can release. So, in theory, you could make a weapon of almost any size by adding more stages to a hydrogen bomb.
So a Death Star isn't totally impossible if you just think about the physics?
If you're just talking physics, maybe not. But remember, building something that huge would be a massive engineering challenge. And there are a lot of ethical issues, too. And honestly, I think it's safe to say we're a long, long way from that, which is probably a good thing.
Okay, well, let's talk about something a little less destructive. Teleportation. It's a classic sci-fi idea, but is there any real science behind instantly transporting matter from one place to another?
This is where things get really wild because teleportation kind of challenges everything we know about physics. In classical physics, the world of everyday objects, teleportation is a no-go. Matter can't just vanish from one spot and pop up in another. But when you get into quantum mechanics, well, things get a lot weirder.
Quantum mechanics, the world of tiny particles and crazy probabilities, isn't that where cats can be both dead and alive at the same time?
You got it. And that's where teleportation starts to find some footing. In the quantum world, particles can do some bizarre stuff, like something called quantum leaps.
Quantum leaps, I feel like there was a TV show about that back in the day.
Yeah, there was a show called that. But in physics, a quantum leap is when a particle jumps from one energy level to another without actually moving through the space in between.
So are you saying our atoms could just suddenly reassemble somewhere else? Like, poof, we're here 1 minute and gone the next?
Technically, yeah, it's possible. But here's the thing. The chances of that happening randomly are so tiny that you'd have to wait longer than the entire lifetime of the universe for it to happen. It's like winning the lottery 1 billion times in a row.
Okay, so spontaneous teleportation is probably not going to happen anytime soon. But are there other ways to think about teleportation? Ways that don't rely on random chance?
That's where this mind-blowing idea called quantum entanglement comes in. Imagine two particles that are linked together so that whatever happens to one instantly affects the other, no matter how far apart they are.
Wait, so you're saying two particles, even if they're light years away from each other, can be connected and act like one thing?
That's right. It's like they're two halves of the same coin, even if you split the coin in half and put each piece on opposite sides of the galaxy. This spooky action at a distance, as Einstein called it, is one of the weirdest parts of quantum mechanics. But it's also one of the most powerful.
Okay, so how does entanglement connect to teleportation?
It's the key to something called quantum teleportation. But remember, we're not talking about teleporting actual stuff like you see in Star Trek. It's more about transferring the quantum state of one particle to another.
So not beaming someone across the galaxy, but beaming information.
Exactly. Think of it like this. You have two entangled particles, A and B. You want to teleport the information from particle A to particle B, which could be anywhere in the universe.
Okay, so how do you do that?
Well, it's kind of complicated, but basically you measure particle A and then send that information using regular stuff like light or radio waves to wherever particle B is. And because they're entangled, the information about particle A instantly affects particle B, basically transferring the information from one to the other.
Whoa, so you're not actually moving the particle, you're just sending its information.
That's it. And this isn't just an idea. Scientists have actually done quantum teleportation in labs. They've teleported photons, which are particles of light, across pretty long distances.
So we're teleporting light now, is that what you're saying?
Yep, but it gets even crazier. Scientists have recently done something amazing. They've teleported atoms, not just photons.
Atoms? Seriously, how is that even possible?
They use something called Bose-Einstein condensates, or BECs. Imagine a bunch of atoms that are super cooled almost to absolute zero. At that temperature, the atoms start acting like one giant atom, a superatom.
So they're teleporting these super atoms. Does that mean teleporting humans is next? Can I book my flight to Mars yet?
Not so fast. Well, teleporting atoms is a huge deal. Teleporting a person is way, way more complex. We're talking trillions and trillions of atoms that would have to be perfectly entangled and teleported.
Okay, so beam me up, Scotty, isn't happening anytime soon. But just the fact that we're teleporting atoms at all is mind-blowing. Where does this research go from here?
That's the exciting part. We're really just starting to figure out what's possible with quantum teleportation. It could totally change things like computing and communication. Imagine a world where information can be sent instantly anywhere in the universe.
That'd be wild. Super secure communication, faster computers, the possibilities are endless. This has been one heck of a deep dive already. We've talked about force fields, invisibility, the Death Star, and even teleportation. I can't wait to see what other crazy topics are coming up.
Next up, we're going to get into mind reading and psychokinesis. Can we really tap into someone's brain or move stuff with our thoughts? Get ready, things are about to get even weirder.
So we just finished talking about teleporting atoms, which is wild enough. But what about teleporting thoughts? Is mind reading something that could actually happen?
Yeah, that's a question that's always kind of freaked people out, but also made them really curious. The idea of knowing what someone's thinking, like getting inside their head. It's intriguing and kind of creepy all at the same time.
For sure. I mean, think about it. It could be super useful, right? Like imagine being able to talk to someone just with your mind, no words needed. But it'd also be a total invasion of privacy. Like, what would happen to society if we couldn't keep our thoughts secret anymore?
Kaku talks about those ethical issues too. But if you just look at the science, the question is, can we really read minds? And if we can, how?
Well, didn't the CIA try to do that back in the Cold War with some psychic stuff? Project Stargate or something?
Yeah, Project Stargate was a real program, but the CIA eventually decided it wasn't giving them any useful information. While they were messing around with the paranormal, the real breakthroughs were happening in neuroscience.
Right, with brain scanning tech like EEGs and MRIs. Those can actually show us what's happening inside our brains, right?
Exactly. EEGs, electroencephalograms, they measure the electrical activity in your brain. They've been used for all sorts of stuff, like studying sleep and diagnosing epilepsy.
Yeah.
And even lie detectors, although those are pretty controversial.
So EEGs can tell us about brain activity, but can they actually, decode thoughts?
Not really. They're good at showing general patterns of brain activity, but they're not precise enough to pick out specific thoughts. That's where MRIs come in, magnetic resonance imaging. MRIs use magnets and radio waves to create super detailed pictures of your brain.
I've actually had an MRI before. It's pretty trippy. You lie in this tube and they can see inside your head. It feels like science fiction.
It is pretty amazing.
Yeah.
And the technology is always getting better. Now, scientists are using something called functional MRI, fMRI, which shows not only the structure of your brain, but also which parts are active when you're doing something or feeling certain emotions.
So we can see the brain in action, but can we actually read thoughts? Is that the end goal?
Some scientists think that if we could create a map of the entire human brain, like neuron by neuron, then we might be able to figure out how thoughts work. Imagine a 3D map of all the connections in the brain, a complete wiring diagram.
That'd be insane. But the brain is crazy complex, right? How many neurons are we even talking about?
Over 100 billion neurons, and each one has thousands of connections to other neurons. It's an incredibly complicated network, and mapping it all out would be a huge job.
Sounds like something that would take decades, if not centuries, to do.
It would definitely be a massive project. But even if we could map every single neuron and connection, understanding how those neural patterns turn into thoughts and feelings is a whole other problem. It's like having a map of all the roads in a country, but you don't know the language or the customs of the people who live there.
Okay, so maybe mind reading is still a long way off, but what about moving stuff with our minds? Psychokinesis, that's another sci-fi thing that seems totally impossible.
You're right. The image of Jedi using the Force to move things is pretty cool. But in real life, there's no scientific proof that we can move stuff just by thinking about it.
But haven't there been people who claim to have psychic powers, like bending spoons with their minds or making things float?
Oh yeah, there have been tons of claims, but none of them have held up under scientific testing. When they're tested in controlled conditions, these so-called psychics can't do anything that can't be explained by tricks or illusions.
So no Jedi powers yet. But what about that research program at Princeton? Didn't they study psychokinesis?
You're thinking of the Princeton Engineering Anomalies Research Program, PER. They ran experiments for over 28 years to see if people's thoughts could affect random things, like coin flips or those random number generators.
And what'd they find? Was there any evidence that our minds could actually change those random events?
The results were statistically significant, which means it's unlikely they were just due to chance. But the effects they found were super tiny, and a lot of other scientists don't agree with their findings.
So no definite proof, but maybe a little hint that something weird is going on.
It's definitely interesting. But even the PER researchers said their results didn't prove psychokinesis, for sure.
Okay, so maybe we can't move stuff with our minds directly, but what if instead of trying to move things with just our thoughts, we could use some kind of outside power source? Like maybe we could control machines or robots with our minds.
Now that's an interesting thought. And it's not as crazy as it sounds. We're already seeing brain-computer interfaces that let people control things like prosthetic limbs or even computers just by thinking.
I've seen videos that it's insane. People who can't move their arms can make robotic arms move just by thinking about it.
Exactly. And as that technology keeps getting better, who knows what we'll be able to do. Maybe one day we'll be able to control machines as easily as we move our own bodies.
Okay, let's move on to another topic that's been a big part of science fiction for a long time. Artificial intelligence. Will we ever see machines that can think for themselves, like in all those sci-fi movies?
That's a question that philosophers and scientists have been thinking about for centuries. The idea of creating something like us, something that can think and reason like we do. It's fascinating and also kind of scary.
I remember reading that even the ancient Greeks had myths about mechanical beings. But what about the real science behind AI? When did that start?
The modern field of artificial intelligence really got going with the work of Alan Turing, that brilliant British mathematician who helped crack the Nazi Enigma code in World War II.
Right, he was a code breaker and a pioneer in computer science. But how did he contribute to AI?
Well, Turing was really into the idea of machine intelligence. He thought that if a machine could act just like a human, then we could say that machine was intelligent.
That's the famous Turing test, right? If you can't tell if you're talking to a machine or a human, then the machine is basically thinking.
Exactly. And Turing's work laid the groundwork for a lot of the research in artificial intelligence that came after him.
So how do you actually go about building a machine that can think? Is it just writing really complicated software, or is it more about trying to copy the human brain?
There are two main ways to approach AI, top-down and bottom-up. Top-down AI is about trying to program computers with logic and rules, basically trying to create artificial intelligence through software.
So it's like writing a really, really long and complicated set of instructions for the computer to follow.
Exactly. But the problem with that approach is that the world is incredibly complicated. It's really hard to come up with rules that can cover every possible situation.
That makes sense. What about the bottom-up approach?
Bottom-up AI is different. Instead of trying to program intelligence directly, it's about trying to copy how the human brain works. This means creating artificial neurons and connecting them into networks, kind of like the neurons in our brains.
So it's more about building a hardware system that can learn and adapt instead of just following pre-programmed instructions.
Yeah, that's the idea. And this approach has led to some really impressive results lately, especially in machine learning.
Machine learning, that's where computers learn from data, right? Like those programs that can recognize faces and pictures or translate languages.
Exactly. Machine learning is a really powerful tool, and it's developing super fast. But even with all these advances, AI still has some big challenges to overcome.
What are some of the biggest roadblocks?
One of the most basic challenges is something called the common sense problem. Humans just naturally understand the world around us. We recognize objects, make assumptions, figure out how to act in social situations. But these things that seem simple to us are really hard to program into machines.
Right, like I can tell who my friend is in a crowd instantly, but that's a really tough problem for a computer to solve.
Exactly. And then there's the whole issue of consciousness. We still don't really understand what consciousness is or how it works. So making a machine that's conscious is a challenge that might take a really, really long time to solve, if we ever can.
So are you saying that true artificial intelligence, the kind we see in movies, is still a long way off?
I think it's safe to say that we're still in the early stages of developing AI. We've made some big steps, but there's still a lot we don't know about intelligence, both human and artificial.
This has been a fascinating look at the cutting edge of AI. But let's switch gears and talk about something a bit more cosmic. Are we alone in the universe? That's a question that's been bugging humans for ages.
It really gets to the heart of where we fit in the grand scheme of things. Just look up at the night sky, billions of stars, countless galaxies. The universe is so vast, it makes you wonder if there are other beings out there, looking back at us, asking the same questions.
I remember seeing that movie Independence Day where aliens attack Earth. It's pretty scary to think about. But how do scientists actually search for extraterrestrial life? Do they just scan the skies with telescopes, hoping to see a flying saucer?
It's a bit more complicated than that. One of the main ways is using radio telescopes to listen for signals from space.
Like those giant dish things I've seen pictures of.
Yep, those are radio telescopes. They're incredibly sensitive and can pick up faint radio waves from billions of light years away. Scientists use them to look for patterns in those radio waves that might be a sign of an intelligent source.
So they're listening for a message from ET.
Basically, yeah. The SETI project, the search for extraterrestrial intelligence, has been scanning the skies for decades, hoping to find some sign of alien life. But so far, nothing.
Nothing at all, not even a little blip.
Nothing that can't be explained by natural stuff. Which is kind of disappointing, but also kind of exciting.
Disappointing because we haven't found aliens yet, but exciting because it means there's still so much out there we don't know about.
Exactly. And the search is still going strong. New telescopes are coming online all the time, and we're getting better at detecting those faint signals.
So there's still hope that we might hear from ET someday.
Absolutely. And even if we don't get a direct message, there are other ways to look for life. Scientists are now using telescopes to study the atmospheres of planets around other stars.
Oh yeah, I've heard about that. They're looking for chemicals that might mean there's life there, right?
You got it.
Yeah.
Things like oxygen, methane, and water vapor, those are all gases we associate with life here on Earth. So if we find them in the atmosphere of another planet, it could be a sign that we're not alone.
That would be huge. Imagine the headlines. Scientists discover evidence of life on another planet. But even if there are other planets out there full of life, how would we ever get there? The distances between stars are mind-boggling.
That's one of the biggest problems with interstellar travel, the sheer size of space and the limits of our current technology.
Even with our fastest rockets, it would take thousands of years to get to the nearest star system, right?
You're right, and the energy you'd need for a trip like that is astronomical. We'd need to come up with completely new ways to power spaceships if we want to travel to the stars.
What about those warp drives they talk about in Star Trek? Could we ever bend space-time and travel faster than light?
That's still pure science fiction for now.
Yeah.
But there's some physicists who think it might be possible, at least in theory.
I've heard about something called the Alcubierre drive. Isn't that a theoretical idea for a warp drive?
It is. The Alcubierre drive is based on the idea of warping space-time around a spaceship. It'd be like creating a bubble that lets the ship travel faster than light without actually breaking the laws of physics.
That sounds crazy, but I bet there are some major hurdles to overcome.
Definitely. The Alcubierre drive would need a ridiculous amount of energy, and we'd need to discover some exotic types of matter that we've never even seen before. But it's a cool concept, and it shows that even the most out-there ideas might have some basis in real physics.
Okay, so maybe warp drive is a long way off. But what about other ways to travel really far distances? Did Kaku talk about any other options?
He did. He talked about a bunch of speculative ideas like nuclear rockets, laser sails, and even antimatter engines.
Antimatter engines. Isn't antimatter that stuff that explodes when it touches regular matter?
Yep, that's right. Antimatter is like the opposite of regular matter, and when they come into contact, they annihilate each other and release a ton of energy.
So it's basically the most powerful fuel you could imagine.
Pretty much. And that's why antimatter engines are so interesting for space travel. If we could figure out how to harness that power safely, we could potentially get close to the speed of light.
Okay, now we're talking. Speed of light, spaceships. But even if we could travel that fast, would we ever be able to visit those parallel universes we talked about earlier? Could we step through a portal into another dimension?
Now we're getting into the really mind-bending stuff. The whole idea of parallel universes is still very speculative, and some physicists think it might be impossible, period.
So you're saying that even with super advanced technology, we might never be able to travel to other dimensions?
It's definitely a possibility. But the more we learn about how reality works, the more we realize how much we don't know. And the idea of interacting with parallel universes really pushes the limits of what we understand about physics.
Well, this whole deep dive has been one mind-blowing revelation after another. From force fields and invisibility to the possibility of alien civilizations and parallel universes, it's amazing to think about what the future might hold. But are there any limits to what we can know or achieve? Are there things that will always be beyond our reach?
That's a question that's puzzled philosophers and scientists for ages, and it's the one we're going to tackle in the final part of our deep dive.
Okay, welcome back to the deep dive.
Right.
We've been exploring all these mind-blowing possibilities from Michio Kaku's Physics of the Impossible, force fields, teleportation, even the chance of alien civilizations out there. But now, I think we should tackle the biggest question of all. Are there limits to what we can know? Are there things that'll always be impossible no matter how advanced our technology gets?
Yeah, it's kind of a humbling thought, right? To think that there might be things we'll just never understand, mysteries we can't solve.
It is. We already talked about Class 3 impossibilities like perpetual motion machines and knowing the future, the ones that seem to break the laws of physics. But are those really off limits forever? Or is there a chance, even a tiny one, that those seemingly impossible ideas could become reality?
Well, Kaku compares this to the world of math, which is interesting.
Okay.
In math, there are things that have been proven impossible, no matter how smart you are. For example, there's a theorem that says you can't divide an angle into 3 equal parts using only a compass and a straight edge.
Wait, really? You can't? I feel like I remember trying that in geometry class.
Lots of people have tried, but it's just not possible mathematically. It's been proven, no doubt about it. So yeah, in pure mathematics, there are some things that are absolutely impossible.
Okay, I get it. There are hard limits in math. But is it the same in the real world? Are there things we can say for sure will never, ever happen?
It's tempting to think that way. But if you look at the history of science, there are tons of examples where things that seemed impossible turned out to be totally possible. Kaku even quotes a speech by this physicist, Albert A. Michelson, who won the Nobel Prize in 1907. Back in 1894, Michelson said that all the major discoveries in physics had already been made.
Wow, talk about bad timing.
Right? I mean, within a few years, physics was totally changed by the discoveries of X-rays, radioactivity, and the electron.
Yeah, that's a pretty big miscalculation. I guess it shows that we should always be ready to be surprised by what science can do.
For sure. And that's what makes this whole exploration of the impossible so cool.
Mhm.
We might think we know what's possible and what's not, but the universe has a way of showing us how much we still have to learn.
Okay, so maybe we shouldn't be too quick to say something is impossible, but what about those things that seem to break the fundamental laws of physics, like perpetual motion? Is there any chance that could actually work?
Perpetual motion is a tough one. The laws of thermodynamics, which deal with energy and entropy, are some of the most solid laws in physics. And they pretty much say that you can't create a machine that runs forever without any external energy input.
But haven't people been trying to make perpetual motion machines for ages? Like, it seems like an obsession.
Yeah, they have. And they've come up with some crazy clever designs, but they've all failed. There's always some loss of energy, some friction or something that stops the machine from running forever.
So it's basically a waste of time.
Pretty much. The laws of thermodynamics are really tough to get around. To break them, you'd need to completely change how we understand physics.
Okay, so perpetual motion is probably out.
Yeah.
What about knowing the future? Is there any way that could be real?
Knowing the future is even harder to wrap your head around than perpetual motion. It goes against the idea of causality, that cause has to come before effect.
Right, like the idea that every action has a reaction and things happen in a specific order.
Exactly. Causality is so basic to how we understand the universe that if knowing the future was real, it would completely change everything we know.
It'd be like watching a movie in reverse.
Right.
Effects happening before their causes, it's hard to even imagine.
It'd be a pretty weird world. Some physicists have looked into theoretical possibilities, like these particles called tachons that move faster than light. But there's no proof those particles actually exist, and even if they did, it's not clear that they would mess with causality.
So for now, knowing the future is still firmly in the realm of science fiction, but hey, who knows what the future holds? Maybe we'll discover something that completely changes our understanding of how time works.
That's what's so great about science. It's all about constantly searching for knowledge. Just when we think we figured it all out, the universe throws us a curveball.
Well, this deep dive has definitely been a wild ride. It's been awesome to explore the possible and the impossible. From force fields and invisibility to the mysteries of the brain and the vastness of space, we've covered a lot.
Yeah, we have. I hope this has made people want to keep asking questions, keep exploring, and never stop being curious about the universe and where we fit in.
Absolutely. Michio Kaku's Physics of the Impossible is a great reminder that what seems impossible today might be totally normal tomorrow, and that the search for knowledge never really ends. So keep asking questions, keep exploring, and keep learning. Thanks for joining us on the deep dive.